All right, let's get right into it. For the longest time, we've measured progress in computing by one thing: speed. How fast can we crunch the numbers? But when it comes to modern AI, that's just not the right question anymore. The real challenge, the true bottleneck that's holding these incredible models back, it isn't about thinking faster. No, it's about something much more fundamental, much more physical, just moving the data around.
So if you remember from our last explainer, we tackled the old enemy, time. We figured out how to take all the math an AI model needs to do and let it all happen at once, in parallel. That long, single-file line of calculations, gone. It was a massive leap forward.
But here's the thing. Even with all that math happening simultaneously, the system wasn't really getting any faster. Something else was still waiting, holding everything up. A totally new bottleneck had shown up. And this one wasn't a problem of when things happened, it was a problem of where they were. We had solved for time, but now we had to solve for space.
And that brings us right to the heart of the matter. The new bottleneck, the one that really defines the performance of pretty much every large AI system out there today, is the simple physical act of moving data from point A to point B.
So when we say data, what are we actually talking about? We're talking about the model's weights. You can think of these as the AI's entire library of everything it's ever learned. Millions, sometimes billions of numbers. For an AI to do anything, to make just one prediction, those numbers have to travel from where they live, in memory, all the way over to the compute core, where the thinking actually happens.
And here is the absolute crux of the issue. The math itself, it's incredibly fast. The cores are ready to go, just waiting. But they can't do a single thing until the data, all those billions of weights, actually shows up. It's like having the world's fastest factory workers all standing around, just waiting for the delivery truck to arrive with the materials. The entire system stalls, not because the work is hard, but because the delivery is slow.
Okay, to really get a grip on this, you've got to understand this one core idea in computing. At any given moment, a system is in one of two states. It's either compute-bound or it's memory-bound. And believe me, this distinction changes everything.
So what's the difference? Well, a compute-bound system is what we usually think of as a slow computer. The data's there, it's ready, but the processor is just grinding away trying to finish the math. On the other hand, a memory-bound system is the complete opposite. The math is easy, it would be over in a flash. The problem is the cores are just sitting there, idle, literally starved for data, waiting for it to make the journey from memory.
And this brings us to the single most important takeaway from this whole discussion. Modern AI systems wait for memory, not for math. The whole problem has shifted from calculation to transportation.
So, how did we get here? And why are some chips, like GPUs, so much better at AI than others, like CPUs? Well, it has absolutely nothing to do with which one is smarter. It's all about the architecture. It's all about the size of the pipes.
This chart really lays out the two different philosophies. A CPU has just a few, but very powerful, very complex cores. It's built for intricate tasks that happen one after another. But look at its data pipe. It's narrow. It expects data to arrive in these small, neat little packets. A GPU, though, is the opposite. It has thousands of simpler cores, but its data pipe is like a massive fire hose. It's designed to handle a torrential flood of data all at once. And for AI, that narrow little CPU pipe becomes its Achilles heel.
This is the classic failure mode for a CPU trying to handle a big AI model. Its super smart cores are just sitting there, totally capable, ready to work, but they're waiting. The cores are ready, the data is not.
So the reason GPUs totally dominate the world of AI isn't because their cores are better or faster. In fact, individually, they're much simpler. The entire advantage comes down to the plumbing. It's not about smarter cores, it's about wider pipes. And that brings us to the key difference. This is not speed, this is bandwidth. It's the sheer ability to move an enormous amount of data all at the same time. Now, this memory problem was always kind of bubbling under the surface. But then, one specific innovation in AI research came along and turned it from a nagging issue into the single biggest challenge we face. And that was the invention of the attention mechanism.
Which leads to the obvious question, right? What was it about this attention thing that suddenly made having these massive, wide data pipes an absolute necessity?
The answer is right there, the rise of the attention mechanism. This is the engine that powers all modern transformer models. Like the large language models everyone's talking about. Attention completely rewrote the rules of the game.
Here's how. We already said attention let us do the math in parallel, so we weren't waiting in time anymore, but that came with a price, a huge one. To understand a sentence,
The model now needed to look at the relationship between every single word and every other word in that sentence, all at the same time. This caused an absolute explosion in the amount of data that had to be moved for every single step. Attention traded time dependency for data hunger. And this new reality, this incredible hunger for data, it completely flipped the script on how we design computer chips. The problem wasn't, how do we compute faster anymore? The new problem was, how do we physically get the data to the compute cores fast enough to keep them busy? You can literally see this evolution just by looking at the hardware. A classic CPU puts a few powerful cores right in the middle, and the memory is kind of off on the periphery. Then GPUs adapted that by just making the data pathways much wider to feed all their cores. But today's AI accelerators, they take it to the logical extreme. The whole chip is designed from scratch around one single principle: make the physical distance that data has to travel as short as humanly possible.
The result is profound. The physics of just moving information became so important that we had to completely reorganize the silicon itself, all for the sake of data movement.
Okay, let's put it all together. What is the one thing that is truly limiting the AI systems we have today?
The logic, when you lay it all out, is actually pretty simple. 1, the math is fast. Our compute cores can handle it. 2, the data, all those model weights, is heavy and it lives far away in memory. 3, attention, the heart of modern AI, needs a ridiculous amount of that data at every single step. The conclusion is just unavoidable. Bandwidth, how fast we can move that data, is what truly limits AI performance.
And that leaves us with this one final thought. It's a total reversal of how we've always thought about performance, but it's the new reality. In AI, the pipe matters more than the brain.
So the solution seems simple, right? Just add more chips, get more bandwidth. For a while, that worked. But that strategy of just scaling up eventually slammed into a brand new wall. In our next explainer, we'll dig into what happens when the problem isn't just the pipe, but when you start to run out of the data itself.